Hey everyone, and welcome back. Today, we've got an absolutely fascinating journey ahead of us. We are going to completely master Chapter 5 of your geography textbook, Minerals and Energy Resources. So grab your notebooks, get comfortable, and get ready, because by the end of this explainer, you're literally going to see the world around you in a completely different light. Let's dive right in and crack this chapter together. Take a second and just look around your room right now. Look at your phone, look at the screen you're watching this on, or, just look up at a simple light bulb. Have you ever dug a little deeper and thought about what's actually inside them? We take these everyday objects totally for granted, but how many minerals do you think are used to make just one simple light bulb? Think about the glass, the filament, the wiring. It's an absolute hidden geological masterpiece. Everything we build, everything we use, it all relies on materials pulled directly from the earth. And it gets even more personal than light bulbs or smartphones. All living things need minerals. But here's a totally mind-blowing fact for you. Our mineral intake represents only about 0.3% of our total nutrient intake. Just 0.3. But they are so incredibly potent and so fundamentally important that without that tiny 0.3%, our bodies wouldn't even be able to utilize the other 99.7% of the food we eat. Without minerals, life processes simply cannot happen. No way around it. So, since they're quite literally vital to our survival and our entire civilization, we need a solid game plan to understand them. Here's our roadmap for today's explainer. First, unlocking the mineral world. Second, where do minerals hide? Third, major Indian mineral reserves. Fourth, conserving our mineral wealth. Fifth, powering up energy resources. And finally, we'll wrap up with a quick check your understanding. All right, Section 1, unlocking the mineral world. Before we can mine these resources or use them, we really need to know exactly what we're talking about, right? So what exactly is a mineral? Well, geologists have a very specific definition that you definitely need to remember. A mineral is a homogeneous, naturally occurring substance with a definable internal structure. Okay, let's break that down into plain English. Homogeneous just means it's the same throughout. Think of a perfectly blended smoothie, not a chunky fruit salad. Naturally occurring means it's made by the earth itself, not cooked up in some laboratory. And a definable internal structure means its atoms are arranged in a very specific orderly pattern. This unique combination of elements depends entirely on the physical and chemical conditions when it formed. And that's exactly why minerals range from the absolute hardest diamond down to the softest talc. Now, people study the Earth for all sorts of reasons, and there's a really important distinction here in the scientific field that you should know. Imagine you're looking at a huge mountain. A geographer studies the minerals as part of the Earth's crust to get a better understanding of landforms. They really care about where these minerals are distributed and how they impact human economic activities. But a geologist, they want to look onside the mountain. A geologist is interested in the deep science, how the minerals formed, exactly how old they are, and their precise physical and chemical composition. Both roles are super vital, but they have very different focuses. And geologists use all those physical and chemical properties to classify minerals. For commercial and general purposes, we basically group minerals into three big families. First up, we have metallic minerals, which are further split into three types. You've got ferrous, meaning they contain iron, like iron ore and manganese. Then, non-ferrous, which have zero iron, like copper, lead, and bauxite. And finally, precious metals, which are your gold, silver, and platinum. The second big family is non-metallic minerals, things like mica, salt, potash, and limestone. And the third family is energy minerals, the fuels that keep our world running, like coal, petroleum, and natural gas. Make sure you can visualize this breakdown. It's absolutely crucial. Moving right along to Section 2, where do minerals hide? Now that we actually know what they are, where do we find them out in nature? You see, you don't usually just walk outside and trip over a pure, shiny chunk of copper lying on the ground. Minerals are almost always found mixed up with a bunch of other stuff in formations that we call ores. An ore is simply an accumulation of any mineral mixed with other elements. But here's the massive economic catch. The mineral content of the ore has to be in a high enough concentration to actually make extracting it commercially viable. It's kind of like baking a chocolate chip cookie. If there's only one tiny chocolate chip in the entire batch of dough, it's just not worth the effort to dig it out. Plus, the type of formation dictates how easy it is to mine, which directly impacts the cost. So where do these ores actually form? There are four main modes of occurrence you need to lock in. First, in igneous and metamorphic rocks. Here, minerals pop up in cracks, faults, or joints. They form when liquid or gaseous minerals get forced upward towards the surface, and they cool and solidify as they rise. The smaller ones are called veins, and the bigger ones are lodes. This is where you find tin, copper, and zinc. Second, we have sedimentary rocks. Here, minerals occur in horizontal beds or layers. They form from deposition and accumulation over super long periods. Coal is a perfect example of this, formed under intense heat and pressure. Third, placer deposits. These are awesome. They're found in the sands of valley floors and the base of hills. Water washes away the lighter sand, leaving behind heavy minerals that don't corrode. We're talking gold and platinum. And fourth, our vast ocean waters contain gigantic quantities of minerals, though most are way too diffuse to be worth extracting, except for things like common salts, magnesium, and those fascinating manganese nodules on the ocean floor. Okay, Section 3, Major Indian Mineral Reserves. We've talked about how they form globally. Now let's zoom in on our own backyard and see what India has to offer. India is actually super fortunate to have fairly rich and varied mineral resources, and they're mostly concentrated in our peninsular rocks. Let's look at a true heavyweight, iron ore. Iron ore is the basic mineral and the absolute backbone of all industrial development. India is rich in really good quality iron ores. You've got magnetite, which is the finest quality with up to 70% iron content and incredible magnetic qualities. And then hematite, which is the most important industrial iron ore. When you look at the numbers for 2018 to 2019, a staggering 97% of India's iron ore production came from just 4 states: Odisha, Chhattisgarh, Karnataka, and Jharkhand. That is a massive concentration of our industrial backbone in just one region. Now let's jump over to a really cool non-metallic superstar, mica. Mica is fascinating stuff. It's made up of a series of plates or leaves, and it splits so easily that you could layer 1,000 sheets into a pile just a few centimeters high. But why do we care so much about it? Well, because of its excellent dielectric strength, low power loss factor, incredible insulating properties, and resistance to high voltage. Mica is arguably one of the most indispensable minerals used in the electric and electronic industries today. Without it, our modern electronics would seriously struggle to function safely. Which brings us to Section 4, conserving our mineral wealth. We are digging up these incredible resources faster than ever before to support our booming industries. And that brings up a huge issue. Listen to this incredible reality check straight from the text. The total volume of workable mineral deposits is an insignificant fraction, i.e. 1% of the Earth's crust. Just 1%. We are rapidly chewing through mineral resources that took the Earth millions of years to create and concentrate. These geological processes are so agonizingly slow that the rate of replenishment is basically zero compared to how fast we're consuming them. Minerals are finite. They are non-renewable. They're valuable for sure, but they are short-lived possessions. And remember, the more we extract, the deeper we have to dig. That means costs go way up and the quality of the ore goes way down. Because of this, we can't just keep digging blindly. We have to make a concerted effort. There are 3 super clear steps for conservation that we need to follow. First, we absolutely must use our resources in a planned and sustainable manner. Second, we have to constantly evolve our technologies so we can actually use low-grade ores at low costs, rather than just wasting them. And third, we need a massive focus on recycling metals, using scrap metals, and finding other substitutes. Guys, these aren't just nice ideas. They are absolutely essential steps if we want to ensure we have minerals for the future. All right, Section 5, powering up with energy resources. We've covered the materials we use to build things. Now let's talk about the fuel that makes it all run. Energy is literally required for everything: cooking, lighting, propelling vehicles, and driving massive machinery. We basically split energy resources into 2 big buckets: conventional and non-conventional. Conventional sources are the traditional ones we've relied on for a long time: firewood, cattle dung cake, coal, petroleum, natural gas, and electricity. It's pretty interesting that firewood and cattle dung cake still meet more than 70% of the energy requirements in rural households. Though, to be fair, this is being discouraged now to protect our forests and save that valuable manure for agriculture. And coal? Coal is by far our most abundantly available fossil fuel in India. Then, on the flip side, we have non-conventional sources, the renewable energy of the future. This includes solar, wind, tidal, geothermal, biogas, and atomic energy. India is incredibly blessed with an abundance of sunlight, water, wind, and biomass, so our potential here is absolutely huge. Let's shine a quick spotlight on one of those really fascinating non-conventional sources: nuclear or atomic energy. How does it actually work? Well, it's obtained by literally altering the structure of atoms. When you alter that structure, a massive amount of energy is released in the form of heat, and we use that heat to generate electric power. And what fuels this incredible process? Uranium and thorium. Here in India, we have reserves of these in Jharkhand and the Aravalli ranges of Rajasthan. Also, the monazite sands of Kerala are famously rich in thorium. It is an incredibly powerful alternative to traditional fossil fuels. All right, Section 6, check your understanding. We have covered a massive amount of ground today. It's time to put your brains to the test to lock in this learning. Get ready, here we go. Here's your first challenge, a quick multiple-choice question. Which one of the following minerals is contained in the monazite sand? Is it A, oil, B, uranium, C, thorium, or D, coal? I literally just mentioned this a few seconds ago. Think about the beaches in Kerala. Think about atomic energy. Go ahead and lock in your answer. And the answer is option C, thorium. Fantastic job if you nailed that. Remember, the monazite sands of Kerala are a vital resource for India's atomic energy program, specifically because of this mineral. Active recall, just like this, is the absolute best way to master geography. Okay, let's push a little harder with a short answer conceptual question. How are minerals formed in igneous and metamorphic rocks? Take a deep breath. Visualize the crust of the Earth. Think about magma. Think about intense heat and pressure pushing upwards. How do those minerals settle into the rock? Here is exactly what you need to remember. In igneous and metamorphic rocks, minerals occur in the cracks, crevices, faults, or joints. They form as liquid, molten, or gaseous minerals are forced upward toward the surface, where they eventually cool and solidify. The smaller deposits are called veins, and the massive ones are called lodes. Congratulations, you have just mastered the core concepts of minerals and energy resources. But before we wrap up, I want to leave you with one final thought. If workable minerals are truly just 1% of the Earth's crust, and they take literally millions of years to form, how will the cities of the future be built and powered when that 1% finally runs out? The brilliant engineers and geoscientists who are going to solve that problem are sitting in classrooms right now. Keep studying, keep asking big questions, and I will see you in the next explainer.